Good evening. We are ready to go, but a lot of people are yet to come in. So we'll wait for a couple of minutes, not long, but maybe 2 or 3 minutes, and then we'll start. Sorry, I didn't realize I was muted. I had started. Good evening once again. This is SK Ghosh. I would like to welcome you to the continuation of our training and capacity building program under component S9 of RAJUK's Urban Resilience Project. Most of you, I'm sure, have attended other seminars in this series. We will continue today with earthquake-resistant design of BNBC 2020. It's going to be in two parts, part one today and part two tomorrow. I have quite a bit of material to cover. I am not confident that I will be able to go all the way through to the end. If I'm not able to, we will save the material for tomorrow and see what we can cut out tomorrow. So that's kind of the contingency plan. This slide will very likely confuse you because this is one title slide after another, but it is not misplaced. I put it here to tell you that I will start with a few things that we discussed in module Yeah, so I would like to start with a few things that we discussed in, this was not module S9, I think this was G4 or 5. Anyway, this was a seminar on 6th of April on earthquakes and their effects on structures. And I will start from some of the things that were discussed there. The very first thing is when an earthquake moves the foundation from underneath the structure, which is what an earthquake does. The foundation all of a sudden starts moving every which way. That there is no, it just doesn't move left to right or front to back. It moves every which way at the same time. And the mass of the structure, we have drawn for simplicity a 1 bay, 1 story frame. The mass of the structure cannot readily follow the movement of the foundation. It lags behind and then tries to catch up. So the foundation wants to move, in this case from left to right. The mass cannot or will not, because of what we call inertia. It likes to stay behind. Now, when something wants to move and the structure or something doesn't let it move, that means that a force opposite to the motion is created, and that is the inertia force that we talk about. So earthquakes induce inertia forces in the masses that make up a structure. Earthquake forces are not applied loads. They are not like wind. In BNBC 2020 and other codes and standards, including AC 7, you will see earthquake loads. Earthquake loads simply do not exist. Earthquakes cause inertia forces where the masses are. And that's what we are dealing with in earthquake engineering. If the acceleration at the base of the structure, the ground acceleration at the base of the structure is U sub G double T is not U sub G is displacement of the ground One dot is for first differential that will give you velocity. Second dot is second differential that will give you acceleration. U sub g double dot is acceleration of the ground. The inertia force at mass m is the mass multiplied by the acceleration, except that the force, the inertia force, is in a direction opposite to that of the ground acceleration. That's what the negative sign tells you. Okay. Now in the picture, we said the inertia force is mass times the ground acceleration. In some circumstances, dynamic amplification, and that is because near resonance, which we discussed the other day, if the period of the structure and the period of the ground motion are close, then there is near resonance. In those cases, the dynamic amplification can increase the building acceleration to a value 2 or more times that of the ground acceleration at the base. So the acceleration here, particularly for taller buildings as you go up, can be many times U sub g double dot. It's not necessarily equal. Generally, buildings with short natural periods, those would be short, stocky buildings, tend to suffer higher accelerations but smaller displacements. And if it is taller, more flexible buildings, it is the other way. They suffer more displacements but less acceleration. So we are dealing with inertia forces at the floor, slabs, and the roof where the masses are largely concentrated. Okay, so we are looking at the roof slab of a building. It is subject to inertia forces from left to right because the foundation underneath is moving from right to left. Those inertia forces cause in-plane bending of the roof slab. So in that case, the roof slab is acting as a diaphragm, as we call it. Under the in-plane bending, the top of this edge of the diaphragm develops tension. That edge of the diaphragm develops compression. The edges parallel to the earthquake or the inertia forces develop shear. Those shear forces are transferred to the supporting shear walls or frames. And those shear walls or frames, the so-called vertical elements of the seismic force resisting system, bring the forces down to the foundation, which take them down to the ground, where all loads ultimately belong. Okay, so earthquake engineering really in its essence consists of taking the inertia forces from where they originate, namely the floor and the roof diaphragms, down to the ground underneath the foundation where all forces belong. So we have to provide load paths from point of load application or origin down to soil underlying foundation. This is what the engineer has to do. And these load paths that we as engineers provide better be direct, meaning simple in configuration, and we better provide multiple load paths, not just one, because if something should happen to the one load path that you provided, we don't want a catastrophe. So there should be alternate load path, multiple load paths. And that leads to the concept of redundancy. There needs to be redundancy of load paths. So that was some basic stuff that we discussed the other day. Something else that is very, very basic, and I will go over it one more time, and then we will start into basically today's material. So on this slide, we show the idealized force displacement relationship of a particular structure subjected to a particular earthquake. We are looking at one structure in one earthquake. And initially, we are showing elastic response. Elastic response does not have to mean force proportional to displacement as shown. Elastic really means no residual displacement. The earthquake passes, we get our structure back intact. And importantly, located where it was before the earthquake, not some distance away from where it was. Okay. No residual displacement, meaning no damage to be repaired. We get our structure back intact. Now, this elastically responding structure develops a force F sub u in the process of responding to the earthquake and suffers a total displacement of delta sub u, capital delta sub u. Now, if I were to turn around and say we now are required to design this structure for elastic response to the design earthquake, the immediate conclusion would be that we must provide the structure with a design with a strength at least equal to capital F sub u, the largest force that the earthquake had induced in the structure. If we decide that we cannot afford that high a strength level, that all we can afford is a much lower strength level F sub E, then what will happen if the same earthquake comes hit our structure? As the earthquake-induced forces equal and then exceed F sub E, the structure will start cracking and yielding in places. That will be the end of elastic displacements and the beginning of inelastic displacements, which will not follow a flat top as in my idealized picture, but anyway, the point is that now there is damage associated with the displacements. The earthquake passes, we will not get our structure back intact. The damage will have to be repaired. Now, it is a matter of record. Analytical studies have shown this, observations have shown this. The total displacement suffered by the structure is about the same, not precisely the same as in this idealized picture, but about the same whether structural response is elastic or inelastic to various degrees. Okay. So if we provide a lower strength level than F sub E, we will have higher inelastic displacements. If we provide a strength level higher than F sub E, we will have a lower inelastic displacements. The inelastic displacement cannot be such that our structure will collapse on us. So we should not set the design strength level so low that the resulting inelastic displacement exceeds what we call the inelastic deformation capacity of the structure, the capacity of the structure to withstand inelastic displacements while still carrying full factor gravity loads. Okay. So we can design for the low strength level F sub E, provided the resulting inelastic displacements are within the inelastic deformation capacity of our structure. Inelastic deformation capacity comes from proper detailing of the members and the joints. And that's what the materials chapters of the code are about. So my message to you, and this is something you always have to remember, earthquake design, seismic design, however you want to say it, is a two-part affair. We design for the forces that are given in your case, part 2, chapter 6 of BNBC 2020. But then you also have to detail the structural members and the joints as required by the detailing chapter. It has detailing for concrete buildings, steel buildings, and so forth. The two go hand in hand. The design forces without the detailing requirements have never made any sense. And the bridge between the two, the design force level and the detailing, what kind of detailing we have to do, is the R factor that we will talk about in this presentation. Okay, R is the denominator of the design base shear. The higher the R, the lower the design force level. The higher the need for inelastic deformability, which would require fancy detailing. The higher the R, the lower the design base shear, the lower the need for inelastic deformability, which will allow us to do cruder detailing. So this is the broad picture. Seismic design is essentially a trade-off between strength and inelastic deformability. Okay, so these basics are extremely important to keep in mind. Okay, the seismic design provisions that I will discuss with you are those from the 2020 edition of BNBC, which was gazetted, as you see, on February the 11th of 2021, very recently. And it is, I think, important to point out that the code is dated 2020, but the seismic design provisions, like much else of the structural provisions, are based on ASCE 705. This is the standard titled Minimum Design Loads for Buildings and Other Structures issued by the American Society of Civil Engineers. This is used in the United States as the basis of our codes. It is used in many, many parts of the world. The significant thing is the '05 edition of the standard forms the basis of the seismic provisions of BNBC 2020. That is because the code was substantially complete in 2010, that long ago. So the reference standards are kind of old by now. AC 705, and I found it curious. There is reference to AC 702. So this is 257 equivalent static analysis. This is actually a very important provision. It says alternatively to whatever the BNBC tells you to do, which we will look at, for buildings with natural period less than or equal to 2 seconds, the seismic design base shear can be calculated using ASCE 702 with seismic design parameters as given in Appendix C to BNBC 2020. We'll look at all of that. However, the minimum value of S sub A should not be less than 0.044 S sub ds times I. The values of S sub ds, okay, those details are unnecessary. The point is that reference is made to ASCE 702. And I could not figure out why. In my opinion, this is not the right reference. It should have been ASCE 705 because the design spectrum of ASCE 702 did not have a third branch which was added in ASCE 705. So, but if the period of the structure is less than 2 seconds, it probably does not matter. In any case, I do not know why specific reference was made to ASCE 702. So seismic design provisions of BNBC 2020, which is the focus of our discussion today, is in part 6, chapter 2. The title is Loads on Buildings and Structures. In that chapter, section 2.5 is on earthquake loads. Section 2.7 on combinations of loads plays a major part. And I discussed it the other day. We started with load combinations in our module on gravity loads. Appendix C that just came up in discussion is titled Seismic Design Parameters for Alternative Method of Base Shear Calculation. that plays an integral role in the seismic design provisions of BNBC 2020. So when we talk about seismic design provisions, we have to consider all three of those: Section 2.5, Section 2.7, Appendix C. In AC 705, the base document, seismic design provisions are in chapters 11 through 23. That was not the case in ASC 702. It was in chapter 6 in ASC 702, chapter 9 rather, in ASC 702. In ASC 705, seismic design provisions were reorganized. Since then, they have been in chapters 11 through 23. ASC 7 seismic design provisions are adopted by the International Building Code, and ASC 705 was adopted by the 2006 edition of the International Building Code, and the seismic design provisions are in section 1613 of that code. I have refrained from making too many references to the IBC, but there are a couple that will come up. The detailing rules that I talked about that go hand in hand with the seismic design that is in section 2.5 are in part 6, chapter 8, which is titled Detailing of Reinforcement in Concrete Structure. In that chapter, section 8.3 is earthquake resistant design provisions. That's where the seismic detailing requirements of BNBC 2020 are given. And we will go there. Provisions in this code is to provide guidelines for the design and construction of new structures subject to earthquake ground motions in order to minimize the, okay, in order to, we'll come to later. First of all, it's to provide guidelines for design and construction. A code does not provide guidelines, it provides requirements. So this is kind of a surprise. In the US, this would be an absolute no-no. A code provision has to be enforceable. Anything that is not enforceable doesn't belong in the code. Okay? But BNBC has taken the license to put into the code what would be considered textbook type material. Those are definitely not requirements. So what they say here is what they actually mean. That there is some guideline type language in the code which is not enforceable, which is very different from codes of other countries. So to provide guidelines for the design and construction of new structures is important. The code is for new structures, not for existing structures. Okay, that is a very, very important thing that you absolutely must understand. Existing structures are significantly more complicated, and it is kind of upon by the code. There is a brief chapter, but the code is for new structures. Subject to earthquake ground motion, then in order to minimize the risk to life for all structures, this is one of the purposes or aims to minimize the risk to life, to increase the expected performance of higher occupancy structures as compared to ordinary structures. Higher occupancy structures would be where a lot of people congregate in one space in one place at one time. Schools should be a good example. Where they say higher occupancy structures, they also mean essential facilities like fire stations, police stations, etc. So for those structures, we definitely want to minimize the risk to life, but we also want higher performance than for ordinary structures. So to increase the expected performance of higher occupancy structures as compared to ordinary structures, and to improve the capability availability of essential facilities to function after an earthquake. This is another very, very important thing. So, three things are being said. We want essentially life safety in our structures. That is objective number one. Secondly, we want enhanced performance of all but the ordinary structures, assembly buildings, essential facilities, etc. We also want the essential facilities to continue to function during and following an earthquake. So those are all the objectives of the seismic design that we are doing under BNBC 2020. I think this is very, very nice that the code spells it out in plain, simple language. In the US, we have pretty much the same performance criteria, but they're stated in much more complicated ways, very, very difficult to figure out. It is not, then something very important, it is not economically feasible to design, therefore, to allow inelastic deformation and structural damage at preferred locations within the structure without endangering structural integrity and to prevent structural collapse during a major earthquake. Okay, so this says precisely what I was trying to show you through this picture. Okay, it is not economically feasible to design a structure for this high force level where you will have no damage, elastic response. So we design for a much lower force level, which means that we allow inelastic deformations and damage in our structure. We would like the inelastic deformations to take place at preferred locations, not anywhere they like to happen. Secondly, we do not want the inelastic deformations to be such that the structure will collapse on us. Okay? So BNBC 2020 is spelling it out up front. The intent is therefore to allow inelastic deformation and structural damage at preferred locations in the structure without endangering structural integrity and to prevent structural collapse during a major earthquake. Then BNBC has something that I have not seen in building codes. This is very, very good stuff. And this is why I thought that it would be good to discuss. Characteristics of earthquake-resistant buildings. The desirable characteristics of earthquake-resistant buildings are described below. Structural simplicity, uniformity, and symmetry. Okay, those are the desirable characteristics. Simplicity, uniformity, symmetry. Structural simplicity, uniformity, and plan symmetry is characterized by an even distribution of mass and structural elements, which allows short and direct transmission of the inertia forces created in the distributed masses of the building to its foundation. Okay, short and direct load paths. A building configuration with symmetrical layout of structural elements of the lateral force resisting system and well distributed in plan is desirable. Uniformity along the height of the building is also important since it tends to eliminate the occurrence of sensitive zones where concentrations of stress or large ductility demands might cause premature collapse. Very, very good things are said. So characteristics of earthquake-resistant buildings. Some basic guidelines are given below. These are guidelines. These are not requirements. With respect to lateral stiffness and mass distribution, the building structure shall be approximately symmetrical in plan with respect to two orthogonal axes. The problem with these guidelines is that you as an engineer have very little control over such things. The owner and the architect decide, and chances are very high that you will not get a symmetrical building to design. But at the same time, it is very important for the engineer to know what to ask for, what is good, what is not good. And so you can have an informed conversation with the architect, maybe get some allowances. Okay? Both the lateral stiffness and the mass of the individual stories shall remain constant to reduce gradually without abrupt changes from the base to the top of a particular building. Okay, so masses should remain uniform or change gradually. That again is desirable, but typically does not happen. All structural elements of the lateral load-resisting system, such as cores, structural walls, or frames, shall run without interruption from the foundation to the top of the building. That again doesn't happen. People want their bottom stories, the ground level story, wide open for ballrooms or uh, stores or whatever, and then one level above you start with the walls and the partitions and different occupancy. So all structural elements of the lateral force resisting system shall run without interruption from the foundation to the top of the building. Typically, it is not something that you will encounter. An irregular building may be subdivided into dynamically independent regular units, well separated against pounding of the individual units to achieve uniformity. This is very, very difficult to do, in my opinion. So the suggestion is that you have an irregular building, let us say a U-shaped building. You separate the three units of the U by sufficient seismic joints so that they don't pound against each other. Now you have three regular buildings, but that solution is impractical at many levels. The length to breadth ratio of the building in plan shall not be higher than 4. So so the plan dimension ratio no higher than 4, because the more elongated the building, the more flexible one direction is. This again is nice to say, desirable to have, but more and more in big cities we have leftover lots, very little land. You have no control over the shape of the land. So slender buildings are becoming more and more common. So all the 5 things listed are very desirable, no question about it. At the same time, this is not what you will get most of the time as an engineer to design with, and we have to design what we have to design. We do not have a lot of control over that. Okay, so going into seismic design proper, I start with the seismic input parameter, the ground motion parameters, as we typically call them. Okay? Parameters related to earthquake ground motion. That is the first thing we need to know in seismic design. So section 2.5.4 of BNBC talks about earthquake ground motion. What do I'm trying to figure out what I want to tell you. This section 2.5, in preparing this seminar, I found to be very challenging in some ways. I had talked about it before and I was aware of it, but this time, because I was trying to be comprehensive, it was more of a challenge. it is more of a challenge because the seismic design provisions are basically the same as those of ASC 705, and Appendix C makes that very clear. If you follow Appendix C rather than some of the things in the main body, you are closer to ASC 705. But what is in the main body of BNBC, which is a carryover from the past, gives you exactly the same answer. It's not that you have two different things in Appendix C and in Section 2.5. And I wanted to show you this convergence, that you are talking about the same thing. And that proved to be not so easy to do. I finally had to get down to numbers, work out some numbers that I'll share with you, and you will see that we are talking about identically the same design. The big difference is in AC 705, there are no seismic zones. There are contours of seismic design ground motion parameters, S sub S and S sub 1, as you will see. BNBC continues to use seismic zones, and somehow the ASC 7 ground motion parameters have been made to fit into those seismic zones in a very interesting way. Okay, so I hope to bring all of that out, and that will take time. This is why I don't quite know how timing will go today, but that doesn't matter. So Appendix C is closer to AC 705 than 2.5.4. Both use seismic zones and the same seismic zone map. Okay, both Appendix C and 2.5.4 use seismic zones and the same seismic zone map. Both approaches yield the same seismic base shear. This is very, very important, and I will show you that. No question about it. Okay? Now, this to start with is the design response spectrum, as you see, of ASC 705. A design response spectrum gives you the seismic design force on the y-axis as a function of the period of the structure T on the x-axis. The period is something we talked about a week or two ago. Okay, and I won't repeat. It is a function of the mass and the stiffness of the structure. Okay. I say the y-axis gives you the seismic design force. You look at the picture, you see spectral response acceleration S sub A. That is because the two are related. The design base shear V is the spectral acceleration times mass, or spectral acceleration divided by G, the acceleration due to gravity, multiplied by the weight of the structure. Okay. The design spectrum of ASC 705 consists of a flat top, a descending branch that varies with 1 over T, and then a third branch that varies with 1 over T squared. The flat top is defined by the ordinate of the spectrum at a period of 0.2 second, and that is S sub ds. So the flat top is defined by S sub ds, which is the ordinate to the design spectrum at a period of 0.2 second, and then the descending branch is defined by the ordinate at a period of 1.0 second, and that ordinate is called S sub d1. So two parameters, S sub ds and S sub d1, define the design spectrum of ASC 705. Okay. This period T sub L at which we transition from the second branch to the third branch is given in a map in AC 705. It is called the long period transition period, and the equation of the third branch is given. uh, we how should I say, the two ordinates define the design spectrum. The third branch in some ways is an add-on, and to for you to be able to draw the third branch, all you need in addition to S sub ds and S sub d1 is the period T sub L, long period transition period. So you may the T sub L value in AC 705 is between 4 and 16 seconds. 4 seconds is the period of a 40-story tall frame building. So the third branch typically does not come into play in typical designs. Okay. In Bangladesh, the fixed value of T sub L is 2.0 second. Most of the time, you will stay with the first two branches, and those are defined by S sub ds and S sub d1, ordinates to the spectrum at 0.2 second and 1.0 second. Okay. The design spectrum of AC 705, very, very important. The spectrum that is printed in BNBC, okay, I should have said one more thing. This ramp building up to the flat top is not a branch of the design spectrum. The branches are the flat top, which for those of you in structural dynamics, this is the constant acceleration part of the spectrum. This is the constant velocity part of the spectrum. This is the constant displacement part of the spectrum. This ramp simply takes you from 40% of S sub ds to S sub ds at 20% of T sub 0. So this T sub S, I will show you what it is. T sub 0 is taken as 20% of T sub S, and we go from 40% of S sub ds to S sub ds, starting at 0 period to 20% of T sub S. So this is just a ramp making a transition to the flat top. In BNBC 2020, this is the spectrum, also a flat top, a descending branch, and a third branch. What is T sub S in AC 705 is T sub C here. T sub L is T sub D. T sub 0 is T sub B. There's the ramp. The huge difference between the two spectra is the AC7 spectrum I showed you is the design spectrum. This spectrum is the maximum considered earthquake spectrum. I have not discussed design versus maximum considered earthquake yet. That is to come, but please note that that is the situation. Okay, one is a design spectrum, another is an MCE spectrum. Okay, if you compare the AC 705 spectrum with the BNBC spectrum, apart from the fact that one is design spectrum, another is MCE, the transition periods I told you verbally are as shown here. So what is T sub 0 of AC 705 is T sub B of BNBC, T sub S is T sub C, T sub L is T sub D. Now, the all important quantities S sub ds and S sub d1, which would define the design spectrum of AC 705, are not given directly any place in AC 705 or IBC or anywhere else. What is given and where we start are two related quantities, S sub S related to S sub ds and S sub 1 related to S sub d1. S sub S is the mapped maximum considered earthquake spectral response acceleration at short periods for site class B. Quite a lot is said there. Okay. It is the mapped maximum considered earthquake spectral response acceleration, first of all, MCE acceleration at short periods. Initially, when all of this was being developed back in the 70s, short period might mean 0.2 seconds, sometime 0.3 seconds, some other times. But since then, we have settled on 0.2 seconds. So short period is invariably 0.2 second period. Site class B refers to one of 6 site classes in that we have in it will come up in AC 705. We have site classes A, B, C, D, E, and F, not very dissimilar to the soil types of BNBC 2020, and we will come to that very, very soon. Okay. So S sub S is maximum considered earthquake spectral response acceleration at a period of 0.2 second for site class B, which is soft rock, like the rock of the western United States, California rock, which is the benchmark site class for which U.S. Geological Survey does all their mapping. S sub 1 similarly is mapped maximum considered earthquake spectral response acceleration at a period of 1.0 second. It is also for site class B. For any US location, you can get those quantities S sub S and S sub 1 from the US Geological Survey website, or in the old days, AC 705, there used to be paper maps in AC 7 and in the IBC. Now ASCE issues something called a hazard tool from which you can get those values, S sub S, S sub 1. Okay. Now in BNBC, we do not have contour maps. We have no source of S sub S, S sub 1. BNBC, as I mentioned, uses seismic zones. Bangladesh is divided into seismic zones 1 through 4. 1 is the lowest, 4 is the highest. The lowest has an assigned Z value of 0.12, then 0.20, then 0.28, and for zone 4 it is 0.36. Those Z values how do they correlate with the S sub S and S sub 1 that we were talking about, the maximum considered earthquake spectral response accelerations? In Appendix C of BNBC, the S sub S and S sub 1 values for the different zones are simply listed. Okay, so for zone 1, we have an S sub 0.3, S sub 1 of 0.12, for zone 2, 0.5 and 0.2, and so forth. So if you're using Appendix C, the S sub S and S sub 1 values are given to you, and you can proceed with seismic design using the approach in ASC 705 or what is in BNBC 2020, because they are also related to zones. Now, if you look at the numbers, the writers of BNBC have made S sub 1 always equal to 40% of S sub S. Okay, 0.12 is 40% of 0.3, 0.2 is 40% of 0.5, 0.28 is 40% of 0.7, 0.36 is 40% of 0.9. This is something BNBC has built in. In AC7, S sub S and S sub 1 are independent. We have different maps that give us values. So in BNBC, by relating them, we Appendix C gives you the impression that we have two different values, but we actually do not have two different ground motion parameters in BNBC. It's only one ground motion parameter. It is the whichever you like, S sub 1 or S sub S, the two are related. Okay? S sub 1 value is also identically equal to the Z factor for the seismic zone. So for zone 1, S sub 1 is 0.12, Z is also 0.12. For zone 2, Z is 0.2, S sub 1 is also 0.2. Zone 4, Z is 0.36, S sub 1 is also 0.36. And that is quite proper. The relationship between, how should I say, if you take the short period spectral acceleration, S sub S, divide that by 2.5, you take 40% of that, you get something very close to the peak ground acceleration. Okay, S sub S is MCE level. So if you divide S sub S by 2.5, or you take 40% of S sub S, you get a pretty good approximation of MCE level peak ground acceleration. And that's what the Z value is supposed to be. This is why the Z and S sub 1, which is also taken equal to 40% of S sub S, coincide. They are the same. Okay. So one more time from dynamics, if you take the short period spectral acceleration, S sub S, it is MCE level, divide by 2.5, you get a good approximation of the peak ground acceleration, which will also be MCE level. So for 0.3 S sub S, the peak ground acceleration is 0.12 g. And Z is the same, the peak ground acceleration in zone 1, 0.12. S sub 1 being 40% of S sub S, S sub 1 and Z are identically the same. Hopefully that is clear. I probably repeated multiple times the same thing. Now, Z values are given on the map, but for your convenience, BNBC also gives you this table where you can look up the Z value for more in the country. Okay, so for the city of Dhaka, which is in zone 2, the the Z value is 0.2. The site classes of AC705 are A, B, C, D, E, and F. A is hard rock that you find, that's geologically older rock that you find in the eastern United States. Class B is soft rock like in California. C, D, and E are progressively softer material. F is material so poor that to be able to design any building on it, you need a site-specific spectrum. The spectrum printed in the code will not do. Okay. In BNBC, the site classes are called soil types. The site class A is soil type SA, B is SB, C is SC, D is SD, E is SE. F, however, has been split into S sub 1 and S sub 2. These are all defined. I decided not to go into definition of site classes and the soil stuff because I would like to keep to the structural and between Professor Abedin and Professor Ansari, you will get a good idea of the soil or the geotechnical part. Okay? So A, B, C, D, E, F are SA through S sub E, and then F is S sub 1 or S sub 2. B is the benchmark site class of ASC 705. USGS does all their mapping for site class B. BNBC tells you that site class or soil type SA is the benchmark soil type. Okay, so the quantities, the Z values, what S sub S, S sub 1, all the values that you are given are for soil type SA. This is also a significant difference that you should mark. Okay, B is the benchmark site class for ASC 705. BNBC, the benchmark is soil type SA. Not in AC7, but in the IBC pretty much from the beginning. And these things keep on changing. I have, despite a lot of temptation, I have kept to AC705. And when rarely I made reference to IBC, I kept to 2006 IBC. AC705 was replaced by ASC 710, then ASC 716, and now ASC 722 is right around the corner. So a lot of changes have taken place. Same with the IBC. And once I start going there, there will be no end. So I have stuck to the older stuff, and it has been for me an effort to go back to some of this much older material, but that's what I have tried to do. Okay, so back in the days of 2006 IBC, this was the language in the code. Site class D must be used when the soil properties are not known in sufficient detail unless the building official determines that site class C or F is likely to be present at the site. This is very important because in order to establish your site class, you have to have soil property measurement over the top 30 meters or 100 feet of your site. And that is not, not easily done. So in situations where you may not have measurements, IBC gives you this so-called default site class. It's D unless the building official has reasons to think that you have poorer soil, in which case he may insist your default site class has to be E or F. I have not found a comparable statement in BNBC. So apparently you have to find or establish your site class. Now, the values that are given, whether it is S sub 1, S sub S, or Z, are for the benchmark site class. If you have a different site class at your site, your benchmark is SA, you have SC, then the quantity given in the code has to be soil modified. You have to apply soil modification to the ground motion parameter. That's where the site coefficients come in. AC 705 has two site coefficients, F sub A, short period site coefficient, with which we modify the short period ground motion parameter S sub S, and then the long period site coefficient F sub B, with which we amplify the long period ground motion parameter S sub 1. Okay, the F sub A is a function of the site class and also the short period ground motion at the site of the structure. So the site coefficient depends on the ground motion parameter, how intense the ground motion is. let me go to the next one. Okay, node B for site class F tells you that you need site specific analysis. You cannot use the spectrum of the code and site modification factors. These are details that I will let you read. F sub B, the long period site coefficient, is a function of the site class and the long period ground motion parameter S sub 1. Okay? This is about interpolation and things. Now in BNBC 2020 in Appendix C, we have one second. I have okay. So BNBC 2020 in Appendix C gives you also F sub A and F sub B. F sub B is the short period site coefficient with which in AC 705 will amplify S sub S, and F sub B in AC 705 would amplify S sub 1. In the BNBC, F sub A will apply to S sub S as given in Appendix C. F sub B will apply to S sub 1 as given in Appendix C. But remember, S sub 1 of Appendix C is always 40% of S sub S. Okay? So these are the F sub A values. I would draw your attention to the fact that although we have multiple rows for the 4 seismic zones, the values are exactly the same. It is the values of the site coefficients do not depend on the intensity of ground motion as in AC 705. Those are fixed values. Okay? So F sub A, the short period site coefficient that you see in Appendix C, is also equal to S, the soil factor in the main body of BNBC. They are identically the same. They are dependent only on the site class. There is no dependence on zone or intensity of ground motion. The things I have written underneath are very, very important. Okay, so F sub A of Appendix C is the same as S in the main body, and F sub A and S both are dependent on the site class, not on the zone or the ground motion. F sub B, with which you amplify S sub 1 given in Appendix C. Again, there are 4 zones listed, but the values are exactly the same. Okay? So they are not zone dependent factors. And I have also listed here the ratios between F sub B and F sub A. I will show you, unless I forget, the reason I do that just a little bit later. And the ratios are 1, 1 and a quarter, 1 and a half, 2, and back to 1 and a quarter for site class SE. In the main body of the code, this is table 6 to 16, you have the soil factors given, S. This is the same as F sub A. You can verify if you like. You have your handout, and the 3 points that define the spectrum, T sub B, T sub C, T sub D, those values are given. Okay, so with those values, we have the BNBC spectrum pretty much defined. Now, we have S sub S, S sub 1, we have to have at the beginning of seismic design. We just talked about F sub A and F sub B. We multiply S sub S by F sub A, obtaining S sub MS, soil modified short period ground motion parameter. which corresponds to the maximum considered earthquake. That has not changed. S to start with has been corresponding to maximum considered earthquake. We multiply S sub 1, the long period ground motion parameter, by F sub B, obtaining S sub M1, the soil modified long period ground motion parameter, still corresponding to the maximum considered earthquake. In design, we use 2/3 of those soil modified values. 2/3 of S sub MS is S sub DS, design short period ground motion parameter that would define the flat top part of the design spectrum. And 2/3 of S sub M1 is S sub D1, which will define the descending part of the design spectrum, S sub DS, S sub D1. Okay. The 2/3 is the reciprocal of 1.5, 1 divided by 1.5. Okay. So why is the design ground motion parameters 2/3 of the MCE ground motion parameters? We are basically saying our design earthquake is 2/3 of the maximum considered earthquake. Why is that? 2/3 is the reciprocal of 1.5. 1.5 is supposed to be the lower bound factor of safety built into structures designed by the modern seismic code, which by common acknowledgement dates back to 1973 Uniform Building Code. What we are saying is that structures designed by the 1973 UBC or subsequent codes are extremely unlikely to collapse on us until earthquake ground motion equals and then exceeds the design earthquake ground motion, which back in the UBC days was 500-year return period ground motion. Okay. So 1.5 is the lower bound factor of safety that has been established by analytical studies and observation. So the idea is, if we consistently design for 2/3 of the maximum considered earthquake, the built-in factor of safety or margin of safety of 1.5 would ensure that we will at least barely avoid collapse in the maximum considered earthquake. Okay, so we have a built-in margin of safety of 1.5. So if we design for 2/3 of the maximum considered earthquake, we will at least barely avoid collapse in the maximum considered earthquake. That's where the 2/3 comes from. The problem I'm having is I can't, one second. Okay. I the problem I'm having is I can't read. There is a Anyway, so Appendix C also directly gives you the values of S sub ds and S sub d1. Okay. This table is S sub ds. This would be 2/3 of S sub s times the F sub a. Okay. You see the values, and the next table gives you S sub D1. So if you go by Appendix C, the design quantities are directly given to you, S sub DS and S sub D1. And I have written down here something that is important. You will see that the S sub D1 values that are given are S sub DS multiplied by 0.4. 0.4 is the conversion factor between S sub S and S sub 1, remember? And the F sub B over F sub A quantity that I listed in one of the earlier tables. So So S sub D1 and S sub DS are not independent either. They are related as shown here. Okay. So, and all of this tells you about the convergence between Appendix C and the main body of BNBC 2020. Now, back in the UBC days, as I said, the design ground motion had a return period of 500 years, 475 years, 90% probability of non-exceedance in 50 years. And those days we used to design for life safety in that design earthquake. We wanted to preserve life safety in the design earthquake. People at least had to have a chance to evacuate their building at the approach of the earthquake. In ASC 7 and IBC, we have moved on to the new performance criterion that we just talked about, which is avoiding collapse in the maximum considered earthquake, designed to avoid collapse in the maximum considered earthquake rather than provide life safety in the 500-year return period earthquake. This is a major shift that took place as we went from the so-called legacy model codes to IBC design or ASC 705 design. The maximum considered earthquake, which I haven't defined yet, this is the definition in the source document called the NERC provisions, maximum level of earthquake ground shaking that is considered reasonable to design buildings to resist. Having called it a definition, this is really not a definition because the word reasonable, what is reasonable, that makes it very poor as a definition. This is the declaration of principle. The real definition that was built around this declaration of principle became a two-part definition in AC 705 and the IBC because of the peculiar circumstances of the United States. So coastal California, this is probably not directly relevant, but I would like you to refer back to ASC 705, and I have taken a lot of trouble so that you'll be able to do that easily, go back and forth between ASC 705 and BNBC. I think that gives you a lot more flexibility. ASC 705 has commentary that you can look up. There is support literature and so forth. Anyway, coastal California is the only part of the Earth's crust where the seismic sources, the faults and things that can generate large earthquakes, are known. Seismologists also know by and large the capabilities of those seismic sources. So for coastal California, the maximum considered earthquake is defined as the largest earthquake that can be delivered by the known seismic sources. This is the so-called deterministic earthquake. Okay? Now, elsewhere in the country, where seismologists have nowhere near the same handle on either the seismic sources or their capabilities, they have collectively decided that the earthquake that comes the closest to the deterministic earthquake of coastal California is the 2,500-year return period event, 2% probability of exceedance in 50 years. So most of the rest of the United States, this is the maximum considered earthquake. And the right way to look at the definition of maximum considered earthquake of AC 705 is that it is the 2,500-year return period earthquake subject to a deterministic cap. We do not go beyond the largest earthquake that can be delivered by the known seismic sources. The seismic sources in California are too weak to deliver 2,500-year return period earthquake. So we cap it off at the deterministic earthquake. In Bangladesh, we do not have that problem. So the The maximum considered earthquake of BNBC is the 2500-year return period earthquake period. So that makes things simple. Okay. Coming back to the design response spectrum of ASCE 705. It's the same spectrum we have seen before. The colors have been added, constant acceleration part, constant velocity part, constant displacement part. Also, now we know that the spectrum corresponds to the design earthquake, 2/3 of maximum considered earthquake. The only quantity other than S sub ds, S sub d1 that we need to know in order to define the all three branches, this T sub L long period transition period for the United States is plotted. And you see that the values range between 4 and 16 seconds. Now the BNBC spectrum, I have shown you a number of times. I have also shown the correspondence. Now the important things. So T sub S of ASCE 705, the period at which we go from the flat top to the descending branch, is S sub D1 over S sub DS. Okay. That is also the value of T sub C in BNBC. So T sub C is equal to T sub S. Okay. The T sub L of AC7 you saw is mapped. It is 4 to 16 seconds. In BNBC, T sub D is a fixed 2 seconds. So that part is pretty clear cut. The T sub 0 I mentioned to you is 0.2 T sub S. In BNBC, T sub B is not 0.2 of T sub C. It is larger. It is always larger. How the T sub B values were arrived at, I do not quite know, but I did want to show you this correspondence. T sub C is identically equal to T sub S. T sub D has a fixed value of 2.0 second. T sub B values are given. They are not equal to 20% of T sub C. They are always larger. And I do not know how the values were arrived at. Okay. The equations for these branches, this is not a branch. The equation for this ramp, the flat top, this branch and that branch are given in BNBC 2020. I have given you section numbers, equation numbers. All of that took a lot of time, but I think we'll find it valuable because it's not easy to locate things in the code. Now, in these equations, there is a in all the US codes and standards and much of the rest of the world, 5% of critical damping is assumed. So all the spectra that you will see in ASCE 705 are 5% damped spectra. I didn't even mention that. In BNBC, they have given you an option to use something other than 5% of critical damping. That's what the eta factor is. I will not go into that because it is rarely that we use something other than 5% of critical damping. And the eta is equal to 1 for 5% of critical damping. So in all subsequent discussions, I will use eta equal to 1. This table I have shown you already before. So this basically defines these with the S factors. This table defines the soil dependent spectra of BNBC 2020, and I will remind you that those spectra are still the MCE level spectra. Okay, so this table and this table are the same, except here I don't have the soil factors. And again, I have talked about the relationships, the if you look at it, you will see what I have tried to do. Okay, now with the table, as I said, you have the soil modified design spectra of BNBC defined. And this is what they look like. And I just reminded you, I'll remind you again, these are MCE spectra. Okay. The seismic zone map you have. So I have just repeated the just so that there is, like, I was mixing appendix C and the main body. Here I have repeated the height tables. So appendix C of BNBC 2020 simply consists of height tables, and this I have included here just so that you see that if you follow appendix C, it is a pretty clear-cut path. So this is S sub S, S sub 1. I have mentioned S sub 1 is 40% of S sub S. This is F sub A table. This is F sub B table. This is S sub DS, S sub D1. That's your appendix C. Now, so we in all this time, we talked about the spectrum, design spectrum of BNBC 2020. Let us talk about something extremely important. So uniform building code that comes up in discussion even now. 97 UBC was the last time a US model code had seismic zones in it. Back then we had zone 1 through zone 4. 1 was the lowest, 4 was the highest, and zone 2 had a 2A and 2B in it. And then we went away to the maps of S sub S and S sub 1. Okay. Now, back in the UBC days when we had seismic zones, the zone determined the level of detailing we had to do for our structure. We did ordinary detailing in zone 0 and 1, intermediate detailing in zone 2, special detailing in zones 3 and 4. These zones also determine height limits on structural systems. In zones 3 and 4, we had height limits. Special moment, well, the special shear walls could not be more than 160 feet tall. The level of analysis we had to do as the basis of design depended on the seismic zone in which a structure was located. A structure in zone 4 in many situations had to be designed based on dynamic analysis rather than equivalent static analysis. So the level of detailing, the height limit, the analysis we had to do, all those important decisions depended solely on the seismic zone in which a structure is located. In SC 705, where there are no seismic zones, what drives all those decisions? What tells us the level of detailing that we have to do? The answer is seismic design category. Very, very important term. It combines three things: the seismic hazard at the site of the structure, which is what the zone factor was about, but also the occupancy of the structure, whether it's a hospital or an office building now makes a difference, and very, very importantly, the soils at the site of the structure. That has a major impact on the seismic design category. So it's a combination of three things: the seismic hazard at the site, the occupancy of the structure, and the soil type at the site of the structure. Okay? So, occupancy of the structure, I said, is a component of the seismic design category. AC 705 as well as BNBC has occupancy categories defined 1, 2, 3, and 4. They are defined in table 6.1.1. Okay. The occupancy category 1 is unimportant buildings where no life safety is at stake. Occupancy category 2 is standard occupancy building, apartments, office buildings, and so forth. 3 is assembly buildings where a lot of people congregate in one space at one time. 4, essential facilities or hazardous facilities. In AC 705, the seismic design category is determined first based on short period ground motion. In this table, it's a function of S sub ds. You see that it is the seismic design category depends on the occupancy of the structure and soil modified short period ground motion. The seismic hazard is here, the soil is also here. Okay. And there are design categories A, B, C, and D. We then redetermine the seismic design category of our same structure based on soil modified long period ground motion and the occupancy category. Okay. And whichever is the worst governs. If based on long period ground motion, our design category comes out to be C. Based on long period ground motion, design category turns out to be D. Our design category is D, not C. The worst governs. Okay. Now, I mentioned there are 4 design categories in the table A, B, C, D. There is no design category A in Bangladesh because there is no ground motion. Even in the lowest seismic zone, the ground motion, the S sub ds value is larger than 167 and the S sub d1 value is larger than 067. No design category A in Bangladesh. Now, in the tables, you saw 4 categories that are also design categories E and F, which depend on if this is not the mapped quantity. In the other tables, it was S sub ds, S sub d1. If the mapped long period ground motion parameter S sub 1 equals or exceeds 75% of G, which can happen only in the vicinity of known faults that can generate large earthquakes. Then non-essential facilities are occupancy category E, essential facilities are occupancy category F. In Bangladesh, you do not have S sub 1 values larger than or equal to 75% of G. So you do not have design category E or F. You have only B, C, and D. Okay, remember that for all time to come, B, C, and D. Okay. The seismic zoning map, BNBC 2020 gives you directly the seismic design categories depending upon the site class and the seismic zone and the occupancy. Okay, so this is the table. You don't have to do it twice. Take the worst of the 2. It is given to you and you see that the categories are B, C, and D. There is no A, there is no E or F. So this is the table in BNBC 2020 that will give you your seismic design category depending upon the soil type, the zone, and the occupancy of the structure. Okay. Building configuration, horizontal irregularities, AC 705 table 1231. The counterpart in BNBC 2020 is section 2553. It gives you the same plan irregularities. Then The table of vertical irregularities is table 12.3-2 of ASC 705, and the counterpart is 2553 of BNBC 2020. I would like to discuss this very, very important topic in detail tomorrow. So I have basically no discussion here in this slide set for today. Next part, methods of analysis. In ASC 705, there is a simplified analysis supposed to be standalone. You don't have it and you are better off without it. I never thought much of that simplified procedure, and it's a waste of time to talk about it. So let's forget about that. Equivalent lateral force method, section 12.8 of ASC 705, your section 2.5.7. Modal response spectrum analysis, 12.9 of ASC 7, BNBC 259. Linear response history analysis, chapter 16 of ASC 7, 2510 of BNBC. Nonlinear response history analysis, chapter 16 and 2511. Equivalent lateral force is a static method. The other three are dynamic analysis methods. Okay. Equivalent lateral force procedure is allowed to be used under restrictions. The dynamic analysis methods can be used anytime. Modal response spectrum analysis, I what do I want to say? I probably do not want to spend time, at least today, discussing even in brief terms the dynamic analysis procedures, because time can be utilized for other things. I may at some point come back to uh, telling you very, very briefly about them. Okay. Anyway, so those are the okay. The important thing is this: ASC 705 has, as I said, severe restrictions on the use of equivalent lateral force procedure, and let us look at that. I think this is instructive for you to know. If your design category is B or C, equivalent lateral force procedure is always permitted. ASC 705 will never force dynamic analysis procedure on a design category B or C structure. If it is design category D, E, or F, this light frame and stuff you can ignore. If it is D, E, or F, then there is a major division. Are we talking about buildings taller than 160 feet in height or up to 160 feet in height? Okay. So if it is taller buildings, more than 160 feet in height, then you will get to do dynamic analysis. You will be allowed to do equivalent lateral force procedure only if your structure has no irregularities, no structural irregularity, and in addition, the period is less than, not even equal to, 3.5 times the transition period T sub S, which is T sub T sub C of BNBC. It is S sub D1 over S sub DS. Typically, T sub S is about 0.5. 3.5 times 0.5 is 1.75 seconds. That is the period of a 17 or 18 story tall frame. So taller buildings have to be designed based on dynamic analysis. Shorter buildings can be designed using equivalent lateral force procedure, provided there is no structural irregularity. Okay. If you have buildings up to 160 feet tall, then if you have structures with horizontal irregularities type 1B, that is torsional and extreme torsional, and structures with vertical irregularities 1A, 1B, 2 or 3. 1A is substory, 1B is extreme substory, 2, 3, whatever they are. So those are kind of quote unquote bad irregularities. So if you have a building up to 160 feet tall, if you have one of those bad irregularities, you shall do dynamic analysis. Otherwise, you are permitted to do equivalent lateral force procedure. Okay. In BNBC, very interestingly, equivalent lateral force procedure is allowed provided both of the following conditions are satisfied. Here I see a typo. The building period in the two main horizontal directions is smaller than both 4 times TC. TC is T sub S, remember, and 2 seconds. So smaller than 2 seconds. So smaller than 4 times T sub C or 2 seconds, whichever is the shorter of the two. So essentially, instead of 3.5 transition period, BNBC is saying 4 times the transition period. 4 times transition period will be about 2 seconds, and you will not exceed 2 seconds. So it doesn't say regular buildings, regular or irregular, that's your limit. Secondly, the building does not possess irregularity in elevation. So all vertical irregularities will trigger dynamic analysis. Plan irregularities, however, will not trigger dynamic analysis under BNBC. So this is how BNBC has chosen to do it. It's always kind of interesting to compare. Okay, equivalent lateral force procedure. Yeah, I knew today time will be a problem. I have about a half hour, just a little bit over. So let's see where we go. As I said, I'll add it to tomorrow, and then something I had planned will probably not get done, but that's okay. It's important that you understand everything that we covered together, more than uh, more than covering a larger amount. Okay, so design by shear. That's equivalent lateral force procedure. We start by computing the design by shear, which is a coefficient times the seismic weight of the structure. Okay, seismic weight, W. AC7 has a definition. I will let you read. It has snow in it, which you don't care about. This is the BNBC definition of seismic weight. It's extremely important that you understand the seismic weight is not the same as the weight of the structure. Seismic weight in principle is the weight that will be shaken by the design earthquake. So we typically include a part of the design live load in seismic weight, particularly for storage occupancies, because a warehouse is extremely unlikely to be totally empty when the design earthquake hits. Okay, so seismic weight is the total dead load of a building or a structure, including partition walls and applicable portions of other imposed loads listed below. Live load up to 3 kilonewton per square meter, a minimum of 25%. For live load exceeding that, minimum of 50% of the live load. This is, by the way, much higher than in the US. We include 25% for storage facilities, nothing for other than storage facilities. Total weight of permanent heavy equipment or retained liquid or any imposed load sustained in nature shall be included. So total weight of permanent heavy equipment or retained liquid or any imposed load sustained in nature shall be included. Where the probable imposed loads at the time of earthquake are more correctly assessed, the designer may go for a higher percentage of live load. I have not seen anybody do that. Okay, so the design base shear is C sub S times the weight of the structure. C sub S is given by this spectrum, okay? The design spectrum that you have seen time and again. Now, this elastic spectrum, when it comes to the equivalent static approach, we modify that spectrum in 4 different ways. First of all, the ramp is eliminated. In the equivalent static approach, there is no ramp. The flat top extends back to 0 period. Okay? This is modification number 1 of the elastic design spectrum for the equivalent static approach. Modifications number 2 and 3, we erase the elastic spectrum by the importance factor I, and we lower the spectrum by the response modification factor R. Or the way ASC7 shows it, it is the elastic value divided by R over I. The reason being, the reason we show it that way is that it tells you that in a hospital, a special moment frame will not be designed for an R of 8, which is a lot of inelastic deformation. We will design a hospital using a special moment frame for an R value of 8 divided by 1.5, okay, which will be 5.5 and a third. So we will allow less inelastic deformation. That's the idea. Okay, that becomes transparent. So we raise the elastic spectrum by the importance factor I, we lower it by R. And then the 1 over T or 1 over T squared relationship will give us 0 or near 0 base shear for long periods. We do not want to design for 0 base shear, so we impose lower bound values at long periods. The absolute minimum lower bound is 0.44 S sub ds I importance factor times the seismic weight, never below 1% of seismic weight. Okay, this is the minimum that is applicable in all seismic design categories. There is another minimum that applies where the long period ground motion equals or exceeds 60% of G. In Bangladesh, you do not have that, so let us not talk about that. Okay, so 4 modifications. The ramp is eliminated, the flat top goes all the way back to 0 period. We raise the spectrum by I, lower it by R, and we impose minimum design base shears. This minimum 0.44 S sub ds IW, by the way, was eliminated from ASC 705. You will not see it printed there, but then things happen and we had to bring it back. So that is kind of an important minimum. Remember that. The BNBC spectrum, it is MCE spectrum. I keep on saying, you have seen it many times now. The branches, equations for the branches I have shown you. I have also told you that eta is 1 or 5% of critical damping. And these are the values that define the soil modified MC spectra of BNBC 2020, and you have seen the pictures. Now, the spectral acceleration, which is given in AC7 on the y-axis, in BNBC is 2/3 ZI over R times C sub S. Okay, so this is kind of the design base shear equation, because S sub A times the mass of the spectral acceleration times the mass of the structure is the base shear. or spectral acceleration times the weight, seismic weight divided by g, the acceleration of gravity, is the base shear. So this actually is the design base shear equation of BNBC 2020, 2/3 Z I over R times C sub S. The I over R is the same as in BNBC. We raised the elastic spectrum by R, lowered it by R. The multiplication by Z is because C sub S is for site class A. I'm sorry, the the 2/3 of Z, two-thirds brings the maximum considered earthquake spectrum down to the design spectrum. And the Z value makes it zone dependent. Okay, I think it will become clear as you see the numbers. Okay, so here I decided to run numbers using BNBC 2020, the equations that you saw here. Okay, and the appendix. Okay, so an intermediate moment frame building in Dhaka on soil type SD. Residential apartment building I is equal to 1. Dhaka is in zone 2. S is 1.35 for SD soil. For zone 2, Z is 0.2. These values are given in BNBC. T sub B is 0.2 second, T sub C is 0.8, and T sub D is 2.0 second. So for the range of period from 0 to 0.2 second, from 0 to T sub B, this is the equation of the ramp. Our eta is equal to 1. So in our case, the equation is this. Our S is 1.35. T divided by T sub B of 0.2. That gives us this value for C sub S. So at T equal to T sub B of 0.2 second, C sub S becomes 3.375. We take the 3.375, multiply by 2/3 of Z of 0.2 divided by R of 5 times I of 1, we get a value of 0.9. That means the design base shear is 9% of the weight of the structure. Okay, at T sub B, where the ramp meets the flat top. Then the flat top, 0.2 second up to 0.8 second, T sub B to T sub C. This is the equation of the flat top. Our eta is 1, so our equation is 2.5 times S. Our S is 1.35, S is 3.375. We 2/3 Z divided by 5. We have 9% value for C sub S, and at the end of the flat top, we have 9% value for not C sub S, for S sub A, spectral acceleration. Then the descending branch, T sub C to T sub D, 0.8 second to 2 second. This is the equation of the descending branch. Our eta is 1, so our equation is this. T sub C, so S is 1.35, T sub C is 0.8, so C sub S is 2.7 by T. At T equal to T sub D, which is 2 seconds, C sub S becomes 2.7 by 2 or 1.35. Okay. We take the 1.35, multiply by 2/3, Z of 0.2, I of 1 divided by 5, we get 3.6% for S sub A. And then from 2 second to 4 second, which is the end of the BNBC spectrum, This is the equation. Our eta is 1, so this is our equation. 2.5 soil factor of 1.25 T sub C of 0.8 T sub D of 2 divided by T squared. That gives us 5 divided by T squared. So at T of 0.4 seconds, C sub S becomes 3125. We take that, multiply by 2/3, 0.2 R of 5 and I of 1, we get 0.83% as the design. 0.83% of weight is the design base shear. So 9% of the flat top, we go down to 3.6% at T sub D of 2 seconds, and then we go down to 0.83% at 4-second period. Okay, the minimum design base shear of AC 705, which is not in BNBC, except that for Appendix C, it references it. 0.044 S sub ds times I, S sub ds is Z times S. Okay, S sub ds is Z, which is the I have gone over that. Let me not confuse myself and you. Okay, so 0.44 S sub ds is 2/3 of Z times S. Okay, so S sub ds is 2/3 of Z times S. Z is the Z is the same as S sub 1, which is 40% of S sub S and all of that. So S sub ds is 2/3 of Z times S. So 0.44 2/3 Z of 0.2 S of 1.35 I of 1. That gives you 00792 or 0.79%, which being lower than 0.83%, we are okay. I said this check is not required by BNBC 2020. Now, if we were to do the same problem by AC 705, the first branch should be from 0 to T sub S, which is 0.8 second. This is the BNBC ramp from 0 to T sub S of 0.8 second. Not the ramp, remember the flat top goes from 0 period to T sub S, the transition period. So I'm talking about the flat top here of AC 705. Flat top defined by S sub ds divided by R over I. Okay. S sub ds for zone 2 soil type SD, if you go to BNBC Appendix C, S sub ds is 0.45. You divide that by 5, you get 9%. The descending branch, which goes from T sub C to T sub L or T sub D, T sub D is 2 seconds. The equation of the descending branch is S sub D1 divided by R and T. S sub D1, if you go to Appendix C, is 0.36 divided by 5 and T. So at 2-second period, it is 0.72 divided by T or 0.36, 3.6%, which is identical to what we got by BNBC. The third branch beyond 2 seconds, this is the equation in AC 705. S sub D1 is 0.36 from Appendix C. T sub L is 2 seconds. R sub I, R is 5, I is 1, T squared. So it is 144 divided by T squared. At T equal to 4 seconds, we get a value of 0.9%. That being larger than the minimum of 0.79%, we are okay. And somehow this is the only place there was a little bit of a difference between AC7 and BNBC. By BNBC, we got 0.83%. This is 0.9%. I have not quite figured out where it is creeping in from. They are not identical, but they are very, very close. So the two approaches are really They look different. They are not different. Okay. So in the design base shear equations, we have the period T, we have R, we have I. So we have to discuss all of that. The period can be calculated by, period is a function, remember, of the mass and the stiffness. To start with, before we have designed our building, we do not know the mass and the stiffness. So we cannot calculate period. And without period, we cannot calculate the seismic forces. So it is the classic chicken and the egg situation. Which comes first? So that being the case, our codes give us approximate period with which to begin the process. Okay? And having started with approximate period, having gone part of the way through design, if we want to refine our approximate period, the code enables us to do so. We can calculate period by any rational procedure that is in conformance with the principles of mechanics. Okay? The problem with rationally computed period, however, is that it is a function of the stiffness assumptions that we make. For a concrete structure, by taking cracked section properties and by taking cracked section properties as low as we choose, we are in a position to calculate a period as long as we want it to be, which will then translate into a design base shear as low as you would like to design for. And that is not the idea behind the privilege of rational period computation. That is not supposed to be a license to lower the design base shear as much as you would like. So there is always a limit on rationally computed period. You can calculate as long as you want it to be, but you cannot use any larger than a multiplier times the approximate period. So that is the overall picture. The approximate period is now a coefficient times height. This is the structural height as defined, raised to the power raised to the power something. The something is X in AC 705 and M in BNBC 2020. Okay, these are the coefficients. For moment resisting frames of steel, 0724 height raised to the power 0.8. For concrete moment frame, 0466 height raised to the power 0.9. The things that I have written here are quite important, and I would very strongly urge you to read them. But for the sake of time, I'm not going to dwell on those. Okay. Eccentrically braced steel frames, 0731 height raised to the power 75, and this is extremely important. Everything other than the three systems, 0488 height raised to the power 0.75. Okay, we use this time in and time out. Concrete buildings with shear walls, that is what we use. There is a more complicated formula for concrete and masonry shear walls that you are allowed to use. You never have to use it. If it gives you a longer period than this, you are slightly better off. But we have found that this formula has problems. When the shear walls are narrow and when all these shear walls do not go to the top of the building, this formula gives you sometimes very wrong structural periods. So this formula has been modified in later editions of AC 705. We have made H sub I equal to H sub N. So that term has disappeared, and here H sub I has been made equal to H sub N. So my advice will be stick to the other formula and do not try to use this concrete and masonry shear wall formula. This can give you pretty wrong results. Remember, rationally computed period cannot be taken any larger than a multiplier times the transition period. The approximate period. Okay, so in AC 705 rationally computed period shall be no larger than less than or equal to a multiplier C sub u times the approximate period. The less than or equal to has become that sign, I'm sorry. In BNBC, that C sub u is a fixed 1.4. So you cannot take a rationally computed period any larger than 140% of the transition period. In AC 705, the C sub u is a function of S sub d1, the long period design spectral acceleration, and it goes from 1.4 to 1.7. So BNBC has settled for the lowest number, 1.4. This is important. You can calculate a rational period as long as you'd like it to be, but you cannot use something any larger than 1.4 times the rational period. The 1.4 times the approximate period, I meant to say. Okay. AC7 says something that is pretty important. In force calculations, you are always restricted to no more than 140% of approximate period in your case. In AC 705, that restriction need not apply in drift computations. Because in drift computations, if you go with larger values of period, you will be penalizing yourself. BNBC does not tell you that, so which is no loss. But I did want to point out that in deflection calculations, ASC 7 does not restrict us to the upper bound on rationally computed period. Okay, then the R value. Okay. Looking at that time, I think what will happen is I will probably go all the way up to the bottom of the hour, which will be what, 9:30 in Dhaka. Probably no questions today. Tomorrow I will do the last part on load combinations, which I don't think I'll get to today, and the irregularity, and I'll probably leave it at that. I was thinking of non-structural elements, but I probably will not go there, and that will give us time for question and answer. So let me see if there are a few minutes left. I'll take a few questions, but otherwise that's the way it's going to be. This is a lot of stuff and a lot of important stuff, and I did want to start with the basics, because to me and that is very, very important. Just to run numbers is okay. Now R is in the design base shear equation, but there are also two other very important design parameters, C sub D and omega sub 0, that we have to talk about. Yeah. This is very similar to the picture I showed you in the beginning to tell you that seismic design is a two-part affair. We have the load displacement relationship of a particular structure subject, let us say, to the design earthquake of BNBC 2020. This is the load displacement curve. The lateral seismic force is on the y-axis. The lateral deflection is on the x-axis. If the response were elastic up to the design earthquake, then this would have been the load displacement curve. The force induced in the structure would have been V sub capital E, and the displacement suffered by the structure would have been delta sub capital E. Okay. In reality, this is the curve. Now, so to have elastic behavior in the design earthquake, we would have had to design the structure for a strength equal to V sub E. Our code allows us to design for a much lower base shear V. R is the ratio between the two. V is equal to V sub capital E divided by R. Okay, so that's the R value. We calculate this V by the equations that we just went over, design base shear. We distribute that along the height of the structure in the manner prescribed in the code, and I'll show you that very soon. We analyze our structure under those distributed forces. The resulting deflections at the various floor levels are lowercase delta sub x e, x for floor level x, e for elastically computed. Okay. Now, those elastically computed displacements are not the displacements the structure will undergo if the design earthquake were actually to hit. Our estimate of actual design earthquake displacements, delta sub x, is C sub d times delta sub xc. C sub d is called a deflection amplification factor. It takes us from elastically computed displacements under code prescribed seismic forces to estimated design earthquake displacements. Okay, so R and C sub d. Omega sub 0 is something totally different. Let us say the analysis that gave us delta sub xc at floor level x also gave us 100 foot kips of bending moment at the support section of a beam. Okay, 100 foot kips of bending moment at the support section of a beam. If we want to figure out the very largest bending moment that can happen at that support section under the design earthquake, our estimate of that would be omega sub 0 times 100 foot kips. For a special moment frame, omega sub 0 equal to 3. So if elastic analysis under code prescribed seismic forces gives us a bending moment of 100 foot kips negative at the support section of a beam, the actual negative bending moment that can develop at that section is 300 foot kips. That's what omega sub 0 is about. Okay, it is not a system level factor. It's more like a member level factor. I want to emphasize that. So C sub D R omega sub 0. Just like we talked about benchmark site classes, there are two kind of benchmark structural systems. One is a bearing wall system with special reinforced concrete or masonry shear walls. Those are designed for an R of 5. In ASC 705, you have the same value. The other is special moment resisting frame system. And the R value in ASC 705 is 8. And you have the same R of 8. So those are kind of benchmark systems. And the other systems were assigned R values initially by comparison with those benchmark systems. Now, the structural systems that are defined in ASC 705 and BNBC 2020, the basic seismic force resisting structural systems. There are 4. To the top left is the moment resisting frame system, where beam column frames or slab column frames, as the case may be, carry gravity as well as lateral loads. There are no shear walls doing anything significant for us. Okay, so that is the moment resisting frame system. Then what used to be called in the old days the box system, for a long time now we have called it a bearing wall system, where shear walls carry gravity loads and the same bearing walls acting as shear walls carry lateral loads. Okay, Shear wall by definition is a wall that carries gravity as well as in plane as opposed to out of plane lateral loads. So in a bearing wall system, shear walls carry 100% of the gravity and 100% of the lateral forces, the same shear walls. Okay. Then there are combination shear wall frame systems, which can be designed in two different ways, as dual system or as a building frame system, as we call it. In a dual system, the shear walls and the frames both participate in carrying gravity as well as lateral loads. In a shear wall frame system, we as engineers may not decide that the shear walls will carry 60% of the lateral loads and we will design the frames to carry the remaining 40% of the lateral loads. That is not our decision to make. The structure decides. If you do a proper interactive analysis of the combined structural system under lateral forces, you will see that near the bottom of the structure, almost the entire base shear goes to the shear walls with nothing carried by the frames. And as you go up, the frames pick up more and more with the shear walls unloading on the frames. Okay. You have to design the frames on the shear walls on the basis of that interactive analysis. Okay. They will take different percentages of story shear on the different floor levels. In addition, you have to design the frames independently of the shear walls to carry 1/4 of the design lateral forces. This is the concept of the backup frame that has been with us since the 1971 San Fernando earthquake. If we design the frames based on interactive analysis, the columns at the bottoms of the frames would be very flimsy because remember, at the bottom, entire base shear goes to the shear walls, nothing comes to the columns. We cannot design on that basis. So the columns in the lower levels of the frames are designed based on this 25% of the design base shear having to be carried by the frames. So that is a dual system. In a building frame system, we separate gravity resistance from lateral resistance. We have to have essentially complete frames, essentially complete moment frames carrying substantially all the gravity. The words essentially and substantially are both important. I didn't just throw them in. The frame has to be essentially complete, not necessarily 100.00% complete. And and substantially all the gravity loads has to be taken by the frames. That doesn't mean the weights of the shear walls have to be carried by the frames. Okay, so 100 essentially complete frames carrying substantially all the gravity and 100% lateral force resisting shear walls. Okay, so gravity resistance is separated from lateral resistance. In that type of a system, something very important is deformation compatibility. You have to check and make sure that the gravity frames can continue to carry full factor gravity loads as they deform together with the seismic force resisting system all the way up to the design earthquake displacements. Okay? This deformation compatibility requirement is an integral part of the definition of the building frame system. Everything else that we design falls under the category of undefined structural systems, which have to be designed by comparison with one of the defined systems. That's how the system works. Okay. The R omega sub 0 C sub D values are given in AC 705 table 12.2-1, BNBC 2020 table 62.19. Okay. I have listed the concrete systems moment resisting frame system, dual system with special moment frames, dual system with intermediate moment frames, bearing wall system, and building frame system. Some of the systems listed in AC 705 are not in BNBC. But anyway, this table is for you to look at. I don't know that I will gain anything by spending time. Detailing requirements are given in AC 7 chapter 14. That column doesn't apply to you. There are height limits on all structural systems other than the special moment frame and the dual system featuring the special moment frame. The height limits typically apply to the high seismic design categories D, E, and F. Obviously, you do not have E and F, so your concern is only design category D. So design category D, you do have height limits in table 6.2.19 that you have to deal with. NL is no limit, NP is not permitted, and when you have a number, that is the height limit on the structural system. Combinations of structural systems are talked about in AC7 as well as BNBC. If you have combination in the same direction, moment frame, shear walls, and if the combination is not designed as a dual system, then the rule is that you shall design for the lowest R value of all the systems that are strung together. You have special moment frames and special shear walls strung together. You will have to design for an R of 5, not an R of 8. Okay, so the least value of R for any of the systems utilized in that direction. Deflection amplification factor C sub D in the direction under consideration shall not be less. So C sub D will be the largest, and omega sub 0 also shall be the largest. BNBC doesn't say that, AC 705 says that. If you have different combinations in different horizontal directions, you have special moment frame here, special shear walls there. You design for the respective R, omega sub 0 and C sub D values. Okay, pretty simple. Vertical combinations of structural systems. AC7 deals with it. BNBC, I did not see it mentioned, so I did not go there. Vertical combinations of structural systems. So in the design base shear equation, we had period, we had R, we also had I, importance factor I. These are the I values they depend only on the occupancy category of the structure. This category I should have changed to occupancy category. However, time I spend and trouble I take, there are going to be mistakes in the slide sets. So please change that to occupancy category. Anyway, occupancy category 1 and 2. So unimportant buildings as well as standard occupancy I is 1. Assembly buildings, schools and so forth, 1.25, and essential facilities and hazardous facilities 1.5. Pretty simple. Okay. The design base shear is distributed along the height of the structure in a linear fashion if period is up to half a second. K of 1 in this expression will give you a linear distribution of the base shear going from 0 at the base to a maximum at the top. K of 2 will give you a parabolic distribution, 0 at the base to a maximum at the top. And we use a parabolic distribution for period larger than or equal to 2.5 seconds. Okay? If the period of your structure is between 1.5 and 2 seconds, we interpolate between a K value of 1 and 2, so we will get something between a linear and a parabolic distribution. or you are always allowed to use a parabolic distribution, because that way you're penalizing yourself. You are bringing more of the forces to the top of the building, which will give you more overturning moment for the same base shear. Okay. So this is the distribution of the design base shear along the height of the structure. This is something between a straight line and a parabola, K of 1 and K of 2. This gives you a lateral force at every floor level, which is denoted by capital F sub x for floor level x. Okay. And when we talk about story shear, this is floor level x, this is story x, below floor level x. Story shear in story x is the sum of all the forces above the story. So it will be F sub x to F sub n, all the forces from x to n. That is story shear. How is the, so this is the plan of a building where we have in the up and down direction 2 moment frames and 3 shear walls of unequal length. How is the story shear distributed among the 5 resisting elements, the 2 frames and the 3 shear walls? The answer is in proportion to their relative lateral rigidities. How much force is needed to impart 1 unit of interstory displacement to one of those resisting systems. The higher the force, the more rigid the system, and the larger proportion of B sub x it picks up. Okay, so 2 frames, 3 shear walls, they will share B sub x in proportion to their relative lateral rigidities if the diaphragm itself is rigid. That means the diaphragm, the floor slab acting in plane, does not deflect too much under the lateral forces. Okay, that's basically what it means. If the diaphragm itself is stiff, then the distribution is according to their relative lateral rigidities. If the diaphragm is flexible, flexible versus rigid diaphragm are defined in the code, then the distribution will be according to tributary areas, not the relative lateral rigidities. Okay. Now, the story shear acts through the center of mass, which is pretty much at the geometric centroid of the plan, because mass is, I keep on saying, mainly in the floors and the roof, not so much in the vertical elements like the columns and the shear walls. Okay, so the fact that this shear wall is longer than that shear wall does not move the center of mass from the centroid of the section. Resistance to the story shear acts through the center of rigidity. Center of rigidity is decidedly to the left of centroid, because this shear wall being so much longer than that shear wall, it is much more rigid. Rigidity is proportional to the cube of the length. So the center of rigidity is to the left. That means there is an eccentricity between the center of mass and the center of rigidity, which will cause torsion. This picture is deficient in that the torsion is always resisted not just by the elements in one direction, but also those elements, the perpendicular elements. And I have not brought that into the picture because it would complicate it. But anyway, you get the idea. So that's how torsion comes into the picture. It is not only the story shear, but also the torsion. The torsion will increase the forces in this frame, in that shear wall, and will take away from the forces from those 2 shear walls and the frame. The take away we ignored in design, but the addition we have to consider in design. So torsional moment due to difference in location of center of mass and center of resistance must be considered for rigid diaphragms. For rigid diaphragms must be included accidental. Okay, so when the center of mass and the center of rigidity coincide, if those shear walls were of the same length, that would be the case. Even then, we consider an accidental torsion equal to the story shear multiplied by 5% of the plane dimension perpendicular to the story shear. There was a time when we used to design for actual torsion subject to a minimum of the accidental torsion, but now for a long time we are required to design for actual torsion plus accidental torsion. The actual torsion is now called inherent torsion in ASC 705. So we are required to design for inherent torsion plus accidental torsion. So 5%, I told you what accidental torsion is. Now, if we have a torsionally irregular building, which we will discuss at length tomorrow, we are required to amplify accidental torsion by a factor of up to 3. And we will look at that in more detail tomorrow. So if it is a torsionally irregular building, we will have to design for actual torsion plus accidental torsion amplified by an amplification factor that can be up to 3. Overturning moments are simply the lateral forces at the various floor levels times their height above the base added together. Nothing. This is statistically. This is statics. Okay, but the important thing is BNBC in 72578 tells you the foundations of structures except inverted pendulum structures. This is the only time I saw that inverted pendulum mentioned. It is not defined or anything. At least I haven't. Anyway, let's not go into that. The foundations of structures shall be permitted to be designed for 3/4 of the foundation overturning design moment M sub 0 determined using above equation. You get a 25% discount on that moment. This this is not in a C7. All memories came back. It was in the UBC in the old days, but a long time ago, and I can remember now when it was dropped. But and whether it was 25% or some other number, I can't remember. But we had that a long time ago, and it was kind of interesting to find it. The foundation. This is obviously very important. The foundations of structures, except inverted pendulum structures, shall be permitted to be designed for 3/4 of the foundation overturning design moment determined using above equation. Okay, I have one important part left, the drip check, and then the design, the load combinations. So let us, it is already 9:30 and even not allowing for questions. So let us leave it for tomorrow. I now have a much better sense of time. So tomorrow we would do the drip check, then the load combinations, then the irregularity, and I will give you a slide set for the non-structural elements, but I will not have time to discuss it face to face. And we will make some time for questions tomorrow. Okay, so that's it. Thank you so very much for your attention. Pro has to announce something, so let me go to him. What do I do? Mute myself?
Okay, thank you, Dr. Ghosh. So I have two things to say, two comments. So because today's webinar was not concluded, like the whole slide said, the whole material could not be covered. So I will keep today's quiz up till the end, till the day after tomorrow, basically. So in the normal process, today's quiz would expire tomorrow. but in this case, I will keep it up for until the day after tomorrow. And the other thing is about the quiz for pre-recorded webinars. I'm not sure if anyone attending today is also attending any of our pre-recorded webinars, which are basically on various non-structural items like plumbing and fire resistance and architectural issues. In any case, we have received some emails and some people seems to be a little confused about how the quiz for the pre-recorded webinars work. And they actually work exactly the same way a quiz for live webinars work. So you need to come to the instruction page and go to the link through the instruction page so that your attendance gets logged. And that too needs to happen within a certain amount of time. Typically the quizzes start at 10 a.m. Dhaka time. I'm sorry, not quizzes. The pre-recorded webinars are open at 10 a.m. Dhaka time, and the end time kind of varies depending on the webinar. So you need to start watching it within a certain period of time from that 10 a.m. start time. If you log in after that, you will still see the webinar, you will still see the recording, but your attendance may not be logged. So make sure you log in time at 10 and through the instruction page, and then you should not have any problem attending taking the quiz, because we have received a few emails where people say that, okay, we viewed the recording, but when we try to go to the quiz, it says you did not attend. So there could be two possibilities why that is happening. These are the two possibilities, that either they are not going through the instruction page, because the pre-recorded webinars are on YouTube. It is possible that some people are receiving the YouTube link directly and going to YouTube directly, and so then their attendance is not being logged, or they are going through the instruction page but doing it too late to get their attendance logged. So keep those two things in mind, and everything should be fine. Okay, so that's all I have to say. Thank you. Back to you, Dr. Ghosh. Do you have anything more to say, or?
Yeah, I think most people probably are gone. I would like to thank you very much for listening, and we'll hope to see all of you back tomorrow. Okay, bye.